But I think we now have Sue with us, don't we?
Hi, Sue, welcome. Thank you for joining us today.
Good morning, it's a pleasure.
Good morning. So you're going to be telling us all about the UK Space Agency. We've just been hearing about ESA, but we really want to hear about the UK Space Agency. Thank you so much. Do you have some slides to share with us?
Yes. Okay.
Brilliant.
Right, you got slides?
Yes, we can
right.
see them. Thank you.
Okay, so I've been working for the UK Space Agency since it began in 2010, but I've been working on space for a long time before that, and I started in 1991 on Earth observation before moving on to space science and then exploration. So I'm going to tell you a bit about the projects that I'm working on. I will assume that Dave Parker has covered some of the details of the missions and concentrate on the UK space side of things. And I'm going to do Dave's talk in reverse. So I'm going to start with Mars and then go backwards towards the Earth and cover the Moon. So I've been working on the Mars program for the last 18 years. It's a really exciting program. And what do we want to know about Mars? Well, first, if we're going to send humans to Mars, we need to know that it's a safe environment. There's a lot of radiation, there's a lot of dust. We need to understand that and understand how we can live on Mars safely. Also, there's a faint possibility that there is life on Mars. Could that dangerous sort of those like COVID? Could we get something from that? Or on the other side, if there's life on Mars and an ecosystem, could we damage that? And if we do find life on Mars, how we approach Mars is going to be quite different. What are the resources available on Mars? How do we use that? How can we get there safely? How can we land safely? The atmosphere of Mars is only 1% the density of that of Earth. So it's a lot more tricky landing on Mars. And then how do we get off safely and come back home? We don't want to leave people on Mars. We want them to be able to come back to the Earth and tell us firsthand what it's like. So there's those aspects of Mars that we want to know about because we're want to take people to Mars in the long term, to have astronauts walking on Mars. But Mars is intrinsically an interesting place scientifically. 4 billion years ago, Mars looked very much like Earth. It had a much thicker atmosphere. The temperature was much more kind to life, and there was water. There was a lot of water, and that water is now. But why is Mars now a hostile environment to life? There isn't a magnetic field around Mars now. There wasn't. They believe there was in the past, and that not having a magnetic field means that the solar wind can strip away Mars's atmosphere, and that's potentially one of the reasons why it is so thin now. So 4 billion years ago, when Mars was like Earth, that was the time life emerged on Earth. So did life emerge on Mars? So we want to go back and study the rocks, study the evidence to see if we can find evidence of life. And there is a remote and a very remote possibility that there is still life on Mars. We know life now can exist in more extreme environments that we thought life could have been a decade, 20 years ago. So in those cold regions where there is water, there is the possibility of there still being life. And there's still quite a lot of water on Mars, but it's in the ice form. There could be water under the surface. There is water at the poles. And if you melted that water, it would cover Mars with, I think, with depth of about 35 meters. So relatively, there's quite a lot of water, but it's not in accessible forms. So I'm going to go in chronological order, in that the first exploration mission with ESA to go to Mars was the Trace Gas Orbiter. And this is in the exploration program of the European Space Agency. Most of our work is done with the European Space Agency, and we collaborate with many other countries because that makes these programs affordable. Trying to do it as a country by yourself, these are expensive missions, and sharing the costs, sharing the technology is a key thing. So the Trace Gas Orbiter was launched in 2016. It was the first element of a mission called ExoMars. It was going to start by its primary role will be to take data about the atmosphere and has cameras to look at the surface. Now, the UK element on this mission is mainly on the science role. We provided the UV, ultraviolet visible sensors that was built by the Open University, and the Open University are very strongly involved in the camera called CASIS, which was built in Switzerland. Now, that mission also had on it a test landing technology, which unfortunately the test was not successful. And on that lander, we were involved, UK companies were involved in the parachutes. What's interesting, another interesting fact about Mars is the American rovers have detected methane. And so one of the things the Trace Gas Orbiter is looking at is the methane, because methane could have a biological source. It can also have a geological source. So we wanted to study that methane and try and work out if it was biological or a geological source. Now, what's really interesting, and people find it surprising that it's interesting, that the Trace Gas Orbiter hasn't actually detected the methane. Why is that? What's happening in the atmosphere to mean that we're not detecting the methane? So there's a big mystery around that needs to be solved. So that is now operating. The rover, the ExoMars rover, which was then called Rosalind Franklin, has had some problems in that it was a collaboration with Russia. It was going to be launched in September 2022, but the collaboration has broken down and we need to replace the Russian elements. So our major role of the two missions of the rover, Rosalind Franklin rover and the Trace Gas Orbiter, our large industrial element was that the UK has built the rover vehicle, and so this is for the UK. This is a flagship mission. Not only have we built the rover, we've had a large involvement in the science instrumentation. the panoramic cameras that are on the top of the mast. That is led by the Mullard Space Science Laboratory, which is based near Dorking. And also we've built the detectors for a Raman instrument inside the rover, which is going to be looking at mineralogy. So this rover is going to land on Mars at a place called Oxyoplanum. That's interesting because it has rivers, it has clays, there are sediments, and it's like where you want to go with your rover. It's like fossiling. You want to go where sediments are, because that is where there may be evidence for life. So there's a multitude of instruments on there. Importantly, this mission is the first mission that will be able to drill down to 2 meters in depth. So the other thing that the UK industry has been involved in is developing autonomous navigation. So because it takes up to 20 minutes to send a signal to Mars, what you want to be able to do is do a lot of activity autonomously. So the rover can identify safe routes across the surface. So it should be able to drive at least 100 meters a day if we want to. And we are also involved in the mission management system. So the software that runs the science instruments, the delivery of the samples to those science instruments, that again has been developed in the UK. Now currently, because we have to replace the Russian systems, the launch date has now slipped to 2028. But this has given UK industry another opportunity. So for that landing system, we're developing the parachutes. We're also developing the landing platform. That is the last few meters. It holds the rover on. It's got braking engines, and once the parachutes have been separated from the landing system, those braking engines will make sure that the lander safely lands on a safe piece of ground. So that is a key thing. And then it has the platform that the rover is on, and the mechanisms to put the ramps and the mechanisms to deploy the ramps to get the rover safely off the landing platform. So this is a big thing for the UK. We have had a large involvement. We're developing our scientists to be involved in the mission. We're using the images from CASIS to study the landing area, to work out where the safest places are, where the most interesting places are to take the rover. So that is something to look forward to in the future. Something that is just finished, and not only do we work with ESA, but to a lesser extent, we work with other space agencies, mainly with NASA, but we have had in the past missions with the Japanese Space Agency. So what's our last mission with NASA was the InSight mission. This was a mission to Mars to study the deep interior of Mars, to understand what it's like now, how it's formed, how it is different to Earth, why has Mars evolved in a different way. So looking at the structure, looking at the core, the mantle and the crust. So how was the UK involved with this? Well, the UK built a microseismometer. There are 2 seismometers on board, a French-led one, and this is a traditional seismometer. It weighs about 4 kilograms, and that is the image on the top right. Now that seismometer, it also has contained with it the UK microseismometer, and that's the image on the far right. And the difference is that is really small. That is a pound coin by the side of it. So that's the microseismometer. They work at slightly different frequencies. I will always say that the larger one is more sensitive. You do lose something from going that small. But a key thing on space missions is you are limited by the type of the amount of mass you can take with you. So there are some missions where a microseismometer could be used, but they don't have enough mass for a large seismometer. The 2 working together is a very powerful tool. So this mission landed on Mars in 2018 and has been working for the last 4 years, detecting impacts on Mars. That sends seismic waves through Mars, and measuring those waves tells us what's happening in the interior of Mars. Now, the mission ended December this year, and the issue, which was 2 years longer than the original planned mission, what was the eventual problem was those solar panels, those sort of octagonal solar panels got covered in dust, and the mission wasn't producing enough power to get it through the night. They're still monitoring just in case there's a wind that blows off the dust. It might, but it's unlikely to come back to life. So that has produced a lot of important results. There's a Nature paper about to come out. It shows that the mantle is quite different to the Earth's mantle. There seems to be about 3 layers to the crust, and the core is also quite different. The molten core is quite different to the Earth's core. I can't say too much at the moment until that Nature paper has been published. But this is an exciting mission. It's the first time we've been able to take measurements of Mars's interior. So that's a bit about the Mars programme. We are also involved in Mars sample return. We'll probably talk to you in future Mars days about that in detail. But we have other ambitions. We want to be part of the Artemis programme to explore the moon and take astronauts back to the moon. We want to use that opportunity to undertake world-class science and prepare UK industry for a potential commercial lunar activity. It's beginning to look now that in the long term there will be commercial activity on the moon, and we want to make sure that UK industry is well placed to take advantage of that opportunity. So on the science side, and we are really active at the moment. It's been a very busy year. So last week we delivered the Lunar Thermal Mapper instrument. That's the box on the bottom left. This is looking at the water. It's aimed at identifying areas of water to understand the moon's surface. And that will be launched sometime in 2023. We haven't quite got a launch date, but I think it will probably be towards the end of 2023. As I said, it was delivered this week. It is now being installed, integrated onto the spacecraft. We have another mission where we provided the exospheric mass spectrometer. That was built at the Open University. That technology was developed for the Rosetta mission, and it's now gone on to be used for the moon. So it was delivered last year. It's now integrated on the Peregrine lander. We were hoping it would be launched by now, but the launch has slipped. I think it will probably be in May this year. And this will be the first UK-built instrument to land on the moon. So the pictures on the right show the instrument and the instrument going into the test facility once it had been built to check that it was working all right in lunar conditions. So a key thing about these two instruments is looking at the water. The EMS will be able to help resolve how the water got, what was the origin of the water on the moon, and therefore potential origin of water on Earth. But there's also looking at the water cycle on the moon, and I was surprised by this. I didn't think, I hadn't realised that there was a water cycle on the moon. But the water on the moon, at the moment, it's in shaded areas on the moon, mainly in the polar regions, but there are some shaded areas on the equator, and the water is gradually moving to the poles. So trying to understand that water cycle on the moon, and importantly, between the two of them, identifying where there are sources of water for when we have sustained astronaut program on the moon. Okay, but we're also industry is also involved, and these are a few of the things that we're doing. On the Gateway, the UK is providing the refueling system, and that is an interesting technology because going forwards, we're looking at servicing satellites in orbit, and one of those things could be refueling, so satellites have a much longer lifetime. So that's the main element we're doing on the Gateway. UK companies are doing, I've started to build the first commercial data relay system. It's called Lunar Pathfinder. The image on the top left, that's Lunar Pathfinder. So that has been mainly funded privately, but there has been some help from the UK Space Agency on technology development, initial technology development, and also we are working through ESA by providing a free launch to Lunar Pathfinder, but we're getting that launch from NASA, and we're trading some of the data services to get that free launch. So it's not quite a free lunch because we are providing services, but this is the way many collaborations work on the human spaceflight side, is that you partner up with people and you provide something and they provide something, and together it works. So the other thing we're working on are power systems not using solar power. So what we found that a byproduct from the nuclear industry is the production of americium-241. So we reprocess some of the old used plutonium and we can extract americium-241, and we can use these to produce radioisotope heater units and thermal generators, and they will provide, the heater units typically will provide a few watts, the thermal generator to sort of 20-30 watts. So limited power but sufficient for running instruments and things like that. So on the top right is the RHU being developed by the National Nuclear Labs and Leicester University, and it's in the test facilities at Leicester University. This is and this is important technology for all of our solar system exploration, because what it means is you can go deeper into the solar system. When you get to Jupiter and distances away from the sun, solar panels have to be enormous to produce enough electricity. So using RHUs and RTGs means you are less dependent on solar panels. You can go further into the solar system. And also on places like Mars, it will help for survivability in that it gets very cold at night. You're further away from the sun, so you get less power from your solar panels. So that is the important technology, not just for science instrumentation on the moon, but other missions in the solar system. What's exciting is we've just started work with Rolls-Royce to look at nuclear power on the moon using small nuclear reactors. There's a graphic presentation of what Rolls-Royce thinks their system might look like. This is at a very early stages of development, and that would need to be in partnership eventually with NASA or ESA to take that forward, because it is quite massive and will need launches as well, a large launching system, and also it needs to be integrated into a lunar base. So it's just an element. The countries work together to produce different elements needed for a lunar base. The other exciting thing we're working with a company in Sheffield called Metalysis, who have a process on Earth of producing metal alloys from rock, but what they're powdered metals. But the interesting thing of that process is that their byproduct is oxygen. So we're looking at that process, working with ESA on this process of actually processing lunar regolith to make oxygen. And that oxygen can be used for your astronauts, but also it can be used as rocket fuel. So you're not dependent on taking rocket fuel to the moon to get back, or go beyond the moon onwards to Mars. Right. So this was a slide I thought might be useful, just to show people that you don't have to go to the US to work in space, nor do you have to go to the southeast of the UK. This map shows the different places we have directly funded from the UK Space Agency programme. But there are other companies not involved in, not on here, where there's been indirect funding. So for example, we are currently working with Aberystwyth University, and this map was produced before we worked with, put the grant out to Aberystwyth University, who are working with a company in St Afas. Well, the St Afas will not show because that's a subcontract from Aberystwyth University. But this gives you an indication of the breadth across the country where there are people working in space exploration. So I've only covered exploration because that's the area that I work in. Through the ESA programme, there's also a space science programme. The exploration programme is about where humans might live and work. So we concentrate on the near-Earth environment, the International Space Station, and there we have experiments and involvement on the International Space Station, the Moon and Mars. But space science is doing all the science looking out from the Earth, and I'm just highlighting 3 missions that have had strong UK involvement. There was the James Webb Space Telescope, which was launched about a year ago, and there the UK led one of the 3 instruments, the MIRI instrument looking at the mid-infrared, and that's a survey instrument looking at a wide range of things. Then there's the JUICE mission, and there we have a large science involvement. It was a UK person who proposed that mission, and we are leading the magnetometer instrument, and we are providing detectors for some of the other instruments, and that's going to be launched in April. And then looking to the future, there's the aerial project that is looking at exoplanets, looking at their atmospheres, directly studying their atmospheres. That again was proposed by a UK scientist, and that hopefully will be launched in 2029. These complex space missions sometimes take a bit longer than we originally anticipate to build, but at the moment it is scheduled to be launched in 2029. And there are other elements of space that we're involved with. There is a large Earth observation community looking at the Earth from space. It's very important for the environment, for managing disasters. And also on commercial space, the UK is involved in 25% of the communication satellites that are launched nowadays. So we have a strong industrial space sector. And with that, I'd like to finish my presentation. Thank you. I'll take questions.
Fantastic. Thank you so much, Sue, for that lovely overview of UK involvement. I actually have an entire page of questions here for you because there's so much that I and everybody else online wants to find out, and I'm afraid we're a bit short of time, so I'm going to keep it brief. People have been asking a lot about Rosalind Franklin rover. There's a lot of excitement about what that's going to do when it arrives at Mars. And one of the questions we've had is, why is it important to drill down and get samples from below the surface? And why is that, because we already have Perseverance and that's already taking samples, but the difference for Rosalind Franklin is the drilling, is that right? Why is that important?
It's the drilling, so you can get down 2 meters. Mm-hmm. Importantly, the top models have shown that the top 60 centimeters of the Martian regolith is affected by the radiation. So that can be destroying the evidence of life. So getting down to that 2 meter is really important. And also, if you think about when you're fossil hunting, you want to get down.
Right, and so yeah, sort of thinking back to previous missions, InSight had a little drill on it, didn't it? So maybe it's not the first time we've been.
Yeah, that was to look at the heat flow, to understand how the heat was flowing through the Martian regolith.
Yeah.
Unfortunately, it worked like the Thunderbird's mole, if people can remember the Thunderbird's mole, and sort of inched its way in.
Yeah.
And where they landed, there were the regolith had quite a few large rocks, and you just kept hitting rocks. So unfortunately, it wasn't as successful as we hoped, because they couldn't get it down under the surface.
Fingers crossed for Rosalind Franklin. Another quick one actually for you about these samples, because everyone is pretty excited about getting samples back and what that will look like, and even just taking samples and analysing them on Mars. You mentioned life on Mars to start with, and that's, I think, what got everybody excited on their social media. Thinking about sample return and bringing those samples back again, you mentioned that we don't want to wipe out the aliens by going there and introducing microbes from the Earth, and vice versa. We don't want to bring anything nasty to us. How are we going to tackle that problem as we bring samples back?
Okay, so there's been a lot of thought about this, because you have to treat samples from Mars as if there was life on Mars. That's your starting position.
Okay.
I know it's very remote, but you've got to plan on that. So the mission has been designed that anything that has seen Mars' surface will not see the Earth's surface. It's all been contained. So it will, when it lands, that is contained. It's tested to make sure that it would survive a disastrous landing. And then it will go in a special facility. To make and it's like the facilities that study Ebola, but even more so. So one of the things we're developing in the UK at Leicester University and with a company called TAS is what's called a double-walled isolator. So there are two walls, and it means that whatever happens, well, let's say, if something's breached, then you've always got safety. So if that outer wall is breached, then the samples are still contained, and similarly the other way, which is one step further than the isolators you use for studying dangerous diseases like Ebola.
Gosh, we're going to have to handle those samples really carefully. And even thinking about the distribution of those samples around the world and how they're transported and how they're treated. Fascinating. The samples would only be released outside that facility once they've been sterilised. So you know that there's absolutely no chance. But there are some investigations that you want to do before sterilisation. So you will do those inside the facility. Got it.
Then you can sterilise some of the samples, not all of them, the ones that are going out, and you can send them to things like Diamond and those big research facilities, those facilities that you could possibly take to Mars.
Fantastic. Gosh, this is such a fascinating subject.
It's really exciting in terms of we're coming into this potentially new era, and especially with that deeper drilling, the things that might be found. So this has been absolutely fascinating. Thank you so much for joining us on this year's Mars Day. Thank you.
That's a pleasure. Thank you.
Brilliant. And